Okay, so hopefully my software is now working correctly. If not, then I guess we'll go from there. And I would have wasted a lot of time talking to nobody. But I think it's working, so obviously if you're watching this, then it is. So today we're going to talk about the relativity of length. Last time we talked about time dilation and the relativity of time, and we've done a few examples with the relativity of time. And I think it's important that we understand that, and then this will hopefully be a little easier to understand. So I have a picture down here, but we'll look at that later. I'm going to go off to the side and draw something for us. So we've been using a lot with this timing device where you have, this thing that emits light and it goes to a mirror and then comes back, and that's one tick of our clock. Now imagine we flipped it on its side. So it emits light, goes to a mirror, and it comes back. Except this time, we're moving it parallel to the direction that the light's traveling. So this whole system here is traveling at a velocity u. So the important thing here to know is light is moving parallel, that's the symbol, we could also spell it out, parallel to the direction of motion for O prime, which O prime is the perspective inside this moving system. Okay, so hopefully we can talk about this big confusing drawing that I did. So here at the first one, we have our mirror, that's a distance L from our little light emitter over there. And it's moving at a speed u, this whole thing is. So in this first part, and this is from right here, this is a stationary observer. And this is kind of what he's seeing. So in this first part, we'll say A, the light's being emitted, and it's still a distance L from that device to the mirror, and it's moving at a speed u. Well, at some time later, we'll say delta t1, we get to B. And there, the light hits the mirror, and it's going to start reflecting back. Now, real quick, the distance that the light appears to have traveled, right, we can see as L plus U times delta T1 because it went from here and to here. So that looks to be how far it went. And then over here, we drew the final stage, which is the light returning. So it still moves. The sky's still moving to the right. And now the light's moving towards, it's going into our device now. And that is the second, that's where we have this tick. So there we can see the distance is L minus U times delta T2, where delta T is the distance it's moving back. That's to go from here to there. So it's a lot to take in, but I think it'll make sense here in a moment. I just want you to understand the basics that at A, we'll call this C, the light's emitted. At B, it hits the mirror, and at C, it returns. And also know that this is always a distance L apart, and that it's traveling at a speed U. And then in words, I think it'll make more sense. So according to O, the length of our little clock device, the length of the clock, and by clock, that is from here to here. Length of the clock is a distance L. Now, what's important to note, this is different then the length L naught, and that's measured by O prime, who sees the clock at rest. Who sees the clock at rest. The O prime is kind of inside our little system here. If you notice, I put O prime in that little moving box each and every time. So to him, the clock isn't moving. It's the rest of the world around him moving. Okay. So for picture A, I should say, for picture A, the flash of light, is emitted, and it reaches the mirror in B. Okay, so A, it's emitted. B, it hits the mirror a time delta T1 later. So that's the time for the light to get to the mirror. Now, for this interval, we would say that the distance the light travels would be how fast it travels, so the speed of light is c, times the time, which we're saying is delta T1. So that is one way to think of the distance from here to here. But we could also think of it as this distance plus this distance, right? So we could also think of that as being, this is equal to the length of the clock, which we said is L, plus the speed times delta T1. So those are the same distances, and I hope that kind of makes sense. From here to here is L plus the speed. Or you could also think of it as the time, T1, times the speed, which is just c. So if those are the same, then I can say c. In fact, I'll do this in a different color because we're going to use this a little bit. C times delta T1 is equal to our length plus the speed times delta T1. Okay? Then what happens? Well, then the light travels back. So the light travels back to our device in, that's an awful K, and we'll say time interval delta T2. And the exact same logic applies. We can say that the distance is the rate, which is still c, times the time, which we're calling delta T2. Okay? So that is the time it takes light to go from here to go to here. Well, again, there's a few ways we can think of that. We could think of it as the speed of light times that distance, but we can also think of it using the exact same logic. Using the exact same logic is the length of the clock minus, because of our direction, u times delta T1. So it's traveling less of a distance now, and you can kind of think of it from light's perspective. It's like this whole bit is moving towards you. So there's a shorter distance it really needs to travel. So I'll use this in red too. We can say c times delta T2 is equal to L minus u times delta T2. Oops. Look what I did here. So that was T1. That should be T2. Okay? So I'm going to box these really quick because we're going to need those. hopefully that kind of makes sense on where, I think it makes pretty decent sense where the stuff came from. Okay, so let's solve for time 1 and time 2 for both of them. So I'll call this 1 and I'll call this equation 2. So from equation 1, right, we can see that C times delta T1 minus U times delta T1 equals L. And if we solve for delta T1, right, we could factor that out. Delta T1 equals L over C minus U. And then from 2, right, C delta T2 plus U delta T2 equals our length. And then I'm sure you can kind of see what we're going to get. L over C plus U. Okay? So hopefully that makes sense. Now the total time, so the total time for light to go to the mirror, to be emitted, hit the mirror, and come back, which I'm calling the total time, is delta T1 plus delta T2. And we'll say that's just equal to time, delta T. Well, we found delta 1, that's L over C minus U, plus L over C plus U, which is delta 2. Okay? So let's see, that's L times C plus L times U plus L times C minus L times U. All over something minus something times those same somethings being added. That's just C squared minus U squared, right? The L's U drops. And that's just 2LC over C squared minus U squared. Okay. 2LC over, I'm going to factor out a C squared from the denominator. This drops with one of this. And then this is normally how you'll see it written. Okay. So, coming over here really quick, hopefully that algebra makes decent sense. Delta T is equal to 2L over C times 1 over 1 minus U squared over C squared. Now, this is why it would be helpful to remember the past video, or maybe check it out. Hopefully you remember delta T, when we were working with time dilation, was just delta T naught all over the square root of 1 minus U squared over C squared. Well, those times we should be able to set equal to each other. So this, well, first off, this was also equal to 2 L naught over C times 1 over the square root of 1 minus U squared over C squared. Hopefully you guys were okay because we solved for delta T naught. If you guys remember, we said delta T naught was 2 L naught over the speed. So hopefully you guys remember that. If not, you can just kind of go check it out and you'll be all right. Okay, so we should be able to set these equal to each other, namely this part and this part. So 2 L naught over C times 1 over the square root of 1 minus U squared over C squared equals 2L over C times 1 over 1 minus U squared over C squared. The 2's drop, the C's drop, and let's solve for L. So L is equal to L naught times 1 minus U squared over C squared, which is over, you can think of as being to the first power, divided by 1 minus u squared over c squared to the 1/2 power. Well, we can simplify our exponents. So L equals L naught. 1 minus a half is a half, which is the same thing as a square root of 1 minus u squared over c squared. And here we go. This is our length contraction. I don't know why that's so far away from the word length. There we go. That's length contraction. So, we derived it. Let's talk about it a little bit. O prime, who is at rest with respect to the clock, he measures what's called a rest length. A rest length, L naught, or proper length, kind of like we had proper time, proper length. Now, observers who are in motion, relative to O prime, they'll measure a shorter length. So they'll measure a shorter length. Right? Hopefully that makes sense there. They measure a shorter length. Okay. Important thing to know, this is only in the direction of motion. Only in the direction of motion. So if we look up here, our clock was moving to the right. So it would look like it gets crunched sideways, not up and down, since that's where we're moving. I'm going to attempt to draw a few pictures to hopefully help out. Let's say we have this kind of rocket ship. Now let's say it's going 99% the speed of light. And then in blue, let me see, where's my shape helper? This is Earth. Okay. Well, Earth is measuring, so from Earth's perspective, we're measuring that to be some length, when in reality it might be much longer. And they'll be pretty big. I should turn off the thing real quick. Oops. So in reality, maybe it's this long. Well, I don't actually want a good shape here. And then Earth is kind of crunched up a little bit. It's not as, it's squished a little bit. And from the rocket's perspective, this is going 99% of the speed of light that way. So, just to summarize, in this example, Earth sees a smaller rocket rocket sees a smaller Earth. A smaller Earth. One other thing I want to talk about real quick before we stop talking about it kind of conceptually and we'll start working through problems, not necessarily in this video, but in the next one, is if we look at the equation, imagine what happens when u is much smaller than the speed of light. Well, if that's the case, then it's this number, the c, is going to dominate this whole irrational or this whole rational number. So that would mean that you're going to have a very, very small number. So L is very, very close to L naught. So even if you're going really, really fast, because the speed of light is so fast, if you're dealing with a rocket ship or you're dealing with a bullet or you're dealing with something not going very, very fast, then you're not really going to see any length contraction. It's going to be so incredibly small. In fact, I encourage you to kind of look through it because they'll be absurdly small. The human eye wouldn't even be able to detect it. So for that reason, we don't see this in our day-to-day lives. Now, when u grows, you start seeing noticeable effects. So even if it's not something we see in day-to-day life, it is something that does exist. You have to be dealing with something going very fast, close to the speed of light to really see it. Otherwise, it's not necessary. You're not going to see anything noticeable. So that is kind of the idea. We drew some pictures to conceptualize what's going on. We did some math. We derived our length contraction equation here. We talked about it. We kind of see how it's being squished and why we don't see it every day. Now, in the next video, I think I'm going to do 2 examples of the next video and then go on. So yeah, hopefully this makes sense, and I'll continue doing these.